Let's continue with our third lecture on the design of multi-story RCC office building based on the Nepal National Building Code. In our previous lecture, we modeled our building, including modeling of beams and columns, slab, shear wall, and basement walls. We also looked at definition of materials, cross-section, mass source, load patterns, and load combinations. Today we will continue with the modeling part. We are left with modeling of staircase and then assigning of diaphragms. We also defined diaphragms in our previous lecture, and then we will go to the part of load application. To start with the modeling of staircase, let's go to our AutoCAD plan and look at our diagram here. We see that our staircase is located between these two grids 1 and 2 and A and B. Our staircase starts from this point and the landing width slab is represented here. The width of our staircase is 1.45 meter. This is 1.45 meter and the gap between these two flights is 0.754 meter. This 0.754 meter. And the width of our landing slab is 1.505 meter. 1.505. There are 9 risers, or there are 9 steps, so that means total 10 risers and 9 treads in our staircase. So let's model this staircase first. So let's first draw joints to represent the points from where our staircase starts. So this point here, our first riser is at a distance of 1.452 meter from the center of this column. So go to draw joint objects. Since this is the positive x direction, 1452, and click here. Okay. And then the width of our staircase is 1450 mm. So this will be in negative y direction. Minus 1450 here. Now we have created a reference plane at a height of 1.8 meter. We learned about creating a reference plane in our previous lecture also. So go to your reference plane. This 1.8 meter is the mid height where the landing slab rests. So here we have to draw the point from where our landing slab begins, and our landing slab begins at a distance of 1.505 meter from the center of this column. The width of our landing slab is 1.505 meter. So this will be in negative x direction, minus 1505 here. The width of our staircase is 1.45, that will be in negative y direction, minus 1450 for both of this and this joint. And then the gap between the two flights is minus, let's go to our plan again. The gap between these two flights is 754 mm. So minus 754 for this and for this joint. Then go to our first floor level, and here we will draw again same. We will replicate this joint here. So what we will do is we will just replicate this joint here. And I think after drawing this much joint objects, then you can model our staircase. Let's go to modeling our staircase. For that, go to our base level and select this option, draw floor wall option. Select the property as stair slab and start drawing from here to this point. Then go to our reference plane from here to here and click enter. As we have selected all stories here, this staircase slab is modeled in all stories, as you can see on your left hand side, or you can see on your right hand side. Now we will draw the landing slab here. Landing slab will be rectangular. This is landing slab, and then draw the second slab. Okay, we have to draw a joint here also. So to draw that joint, go to draw joint objects. This will be in positive x direction, 1452 mm, and then click here. Then go to our reference plane, select this draw option. It is stair slab here, here, and then go to our first floor level here and here, and then click enter. And then finally draw our another landing slab here, enter. So our modeling of staircase is complete. What we have to do is we have to go to this topmost floor level and delete these slabs and staircase here, because there won't be staircase at our topmost level. So what we will do is, let me rotate this view, and what I will do is, let me go to select properties, slab section, and stair slab. We will select this and then right click and show selected objects only. So for this top floor we don't need this slab here, and we don't need this inclined slab also. And then okay, let me undo this, because I have selected all stories here. Let me select one story and then delete these. Delete this slab first and then this inclined slab. And let me go to all story and I will delete all of the joints. And then right click and show all objects. So modeling of our staircase is also completed. Let me just check this by rotating this view. Okay, our staircase has been modeled now. Okay, now that we have completed the modeling of staircase, save your model and go to assigning diaphragms. And to assign diaphragms, first go to our plinth level or first floor level. Select all the objects. First, activate this option 1 story here and select all the objects. Assign joints diaphragm D1. Apply. Similarly, go to the story above, second story, select assign joints diaphragms D2. Third story, select assign joints diaphragm D3. Another story, select assign joint diaphragms D4. Above, select assign joint diaphragms D5. Go above, select assign joint diaphragms D6. Go above, select assign joint diaphragms D7. And finally go above, select assign joint diaphragms D8. Okay, diaphragms have been assigned for all floor levels. We defined 8 different rigid diagrams in our previous lecture, and those diaphragms have been assigned to each floor level with a separate name, D1 to D8. Now that we have completed this assigning diaphragms, one final modeling part left is the cantilever. You can see in our architectural plan that there is a cantilever coming out of this grid here between 1, 2 and AB. Beyond this column, the cantilever is at a distance of, first from the center of this column, that means 500 divided by 2 plus 1200 plus 300. Okay, we won't use this 300 because this is just representing the window. We will model a diaphragm of 1200 plus 250, that means 1450 mm. So for that, what we will do is select the option all stories here, go to our first floor level, this is our first floor level, and then first activate the option which is the cross section for that our particular cantilever. That means if we select this draw rectangular floor wall option, here the default property will be, select the default property for now is slab 125, since we are going to draw slab 125 as cantilever. And then select this beam here, 8 frames selected. If you look at the bottom left corner, you can see 8 frames selected. That means frames in all 8 stories. Then use this option, edit, extrude, and extrude frames to cells. That means we want to extrude this frame and make it a cell to any particular direction. And our direction is 1450 mm in negative x direction, so it is negative minus 1.45. We will extrude it only once and then apply and click on OK. And we will draw beam also here, so use this draw beam column option, select the property as beam 300 by 400 and draw beam from here to here and here to here. And you can also, okay, let me define another beam and draw beam at the edge of this cantilever. For that, let's go to define, section properties, frame section. Let me add copy of this beam property. Let us call this cantilever beam, and the size will be 230 over 300. So depth will be 300 and the width will be 230, and then click on OK. Now draw this beam 230, cantilever beam 230 over 300 from here to here. So we have drawn cantilever in all of our floors, from first floor or from ground floor to the 8th floor. Let's go to our architectural plan and see that this cantilever is whether it is present in our last floor or not. So let's see here, we have to look at either the north or south elevation. Okay, let us draw like this and then save the model. If you want to see the extruded view, it is here. Okay, now that we have completed modeling, now we will go to application of load. And in application of load, in load application, first let's go to define option and then go to load patterns. In defining load patterns, we define 4 different types of earthquake loads for both ultimate limit state and serviceability limit state. And we assigned the autolateral load as user coefficient. Now we are left with modifying the factors that has to be used as coefficients. So for that, select the earthquake X ULS and go to modify lateral load. Since this is only X direction, I will uncheck this. Eccentricity ratio we have to take as 10%. If you see it, if you look NBC 105 2020 in clause 5.7, what it says is that the accidental eccentricity can be taken as plus minus 0.1 b. That means 10% of width. So use this as 0.1. And this story range, our earthquake force, let us suppose that our earthquake force will not act on our basement since it is below the ground level. So earthquake force will act from the plinth level to our top floor, that is 7th floor level. And finally, for calculating these factors, we talked about calculation of base shear coefficient in our first lecture itself. You can prepare an Excel sheet by yourself for the calculation of those coefficients. For now, let us see one sample calculation for our current building project. Here is an Excel sheet for the calculation of seismic coefficient as per NBC. Our location of building is Kathmandu. Let us suppose it is Kathmandu. Our structural system is moment resisting concrete frame, and our structural system for ductility and overstrength factor is reinforced moment resisting frame. Our seismic zone factor based on table 4.5 of NBC 105/2020 is 0.35. Let's go to that table 4.5. If you see the table here, different seismic zoning factors have been given for different cities and municipalities. And if you search for Kathmandu, it is 0.35. If your city or municipality is not present in this table, then you can go to the figure 4.3 seismic zoning map of Nepal and derive the value of zoning factor from this map itself. So our zoning factor is 0.35. Our importance factor I have taken is 1.25. 1.25 because it is some sort of assembly building. Although we have called this an office building, since people assemble here, since our architectural plans are drawn, we can know from our architectural plans that the students or candidates assemble in this building to give exams. It is some sort of assembly buildings, and for that assembly building I have taken the importance factor is 1.25. The importance factor 1.25. And the height of the building. If there is only staircase cover at the top, you may ignore the height of that staircase cover. But since we have staircase, not only staircase cover, we have a separate rooms on our topmost floor also. We will include the height of that floor also. So the total height of our building is, let's see here, this is 25.2 meter. So our 6th floor level is at a height of 25.2 meter. If you go to our AutoCAD, and you can also, let me just cancel this. If you hover onto any point here, then you can see that the height of this building is at a height of 28.8 meter, and this 28.8 meter means including the basement. The height of the basement. If we subtract the height of basement here, we get 25.2 meter. So let's use the height 25.2. Currently we are using equivalent static method, and the swell type is D. We discussed about this swell type also in our first lecture. Swell type D is for some places in Nepal, including some municipalities including Kathmandu, Lalitpur, Bhaktapur, Madhepur, Thimi, Kageshwari, Manohara and Tokha. So our swell type is D. Now first we will calculate the period of vibration. Our period of vibration will be 1.25 kT into S to the power 0.75. This kT factor is based on this structural system which you are using. If you see here, the value of kT will be 0.075 for moment resisting concrete frame. This is available in our code also. And this 1.25 is because what it says in our clause 5.1.3, I think 5.1.3, what it says is that the approximate fundamental time period calculated using empirical equation in section 5.1.2, that means this equation here, shall be increased by a factor of 1.25. So I have used here 1.25 into kT into e to the power 0.75. kT will be 0.075 for our moment resisting concrete frame and height is 25.2. We get our time period to be 1.054 seconds. Now there are some symbols here, TA, TC, alpha, K. For that, let us go to our code first and see what are those factors. You can see that in clause 4.1.2 we have spectral shape factor for equivalent static method and for response spectrum method and other nonlinear time history analysis methods as well. What it says is that there are some parameters. Our time period calculation for response spectrum method and equivalent static method is based on these formulas here. There are different factors like alpha, T, TA, TC, K. So if it is our equivalent static method, then the value of TA shall correspond to 0. And if it is our response spectrum method, for different swell types, you take the value of TA here. We calculated the value of T, which is our time period. We got it to be 1.054 seconds. Our value of TA is 0 for equivalent static method, and the value of TC. TC means the upper periods of the flat part of the spectrum. The value of TC for swell type D is 2 here, if you see from this table. So we got the value of T, TA and TC. T means we got 1 second, 1 point something as we calculated. TA is 0 and TC is 2 seconds. So what happened here is that we got the value of TA as 0 and TC as 2, and then the value of alpha. The value of alpha is 2.25. So 2.25. And coefficient that controls the descending branch of the spectrum value of K is 0.8. This is 0.8. So we have got the value of all the parameters here. Now we have to check the condition. If T is less than TA, or if T is greater than or equal to TA but less than or equal to TC, or if the T is greater than or equal to TC and less than or equal to C. And we have to use the value of CST accordingly. Doing that, since we got this condition, the value of our time period is greater than or equal to TA but less than or equal to TC, the value of our CST, this spectral coefficient value, will be alpha only for our second condition. So alpha we got 2.25, so CST will be 2.25. And before proceeding further, here we have acquired the value of ductility factor for ultimate and serviceability limit state. And this ductility factor is based on the type of our structural systems. We have a table like this in our NBC code also, and that table gives us different values of ductility and overstrength factor for different structural systems. Now since ours is a reinforced moment resisting frame, the ductility factor will be 4 and the overstrength factor for ultimate limit state will be 1.50 and for serviceability limit state will be 1.25. So we wrote these values here for 1.5 and 1.25. Now we have the value of CST and these ductility factors. Then we can calculate the elastic site spectra for horizontal loading, which will be CST over CST into ZI. CST, Z means zoning factor, I is importance factor. We have the values of all these three symbols. So we get 0.984. For vertical loading, we will have to use 2/3 into Z, but we won't need this for now. And for elastic site spectra for serviceability limit state is 0.2 into CT. So 0.2 into 0.984 means 0.197. Now after calculating this site spectra value, now we will calculate the base shear coefficient. For ultimate limit state, it is this value of CT divided by the ductility factor for serviceable ultimate limit state and the overstrength factor for ultimate limit strength. We get this to be 0.164. For serviceability limit state, it is this CS value 0.197 divided by this overstrength factor 1.25. We get a 0.158. And we have one exponent related to the structural period K value here. In our code number 6.3, which talks about vertical distribution of seismic forces, we have a formula for the lateral seismic force at each level I. And in this formula, we have a factor K as the exponent of this HI. This K is an exponent related to the structural period. So for a structure having the time period less than or equal to 0.5 second, K is equal to 1. If the time period is greater than or equal to 2.5 second, K equals to 2. And if the time period lies between 0.5 and 2.5 second, we have to determine the value of K by using the method of linear interpolation between 1 and 2. Since our structural time period is 1.05 second, by interpolating between values 1 and 2, we get the value of this exponent as 1.277. Now, these three values are the factors that we need to use in ETABS. First, let's go to define and load combinations. Define and load patterns. And select this EQX, ultimate limit state, and modify lateral load. Our base shear coefficient C means this horizontal base shear coefficient for ultimate limit state 0.164. Since this is EQX for ultimate limit state 0.164, and the building height exponent K will be 1.277. 1.277. Our earthquake force will range from plinth level to the top floor, and the eccentricity ratio 0.1, and we uncheck this Y direction. Click on OK. Similarly, for EQY ULS, modify lateral load, uncheck these boxes for X direction, eccentricity 10%. Now base shear coefficient, since this is also for ultimate limit strength, it will be same 0.164, and building exponent height is 1.277. Story range from plinth level to 7th floor. Okay. Now for serviceability limit state, first this is for X direction, so don't include this Y direction. Eccentricity 0.1 from plinth level to 7th floor. Building exponent height 1.277. Now base shear coefficient will be 0.158. 0.158. Click OK. Again select this EQY SLS, modify lateral load, uncheck these boxes 10% from plinth level. So what we got, the base shear coefficient 0.158 and 1.277. Click on OK, and save your model. Now after completing this, now let's go to assigning loads. We created different type of load patterns in our previous lecture, including dead load, different types of live load, floor finish, masonry, partition, swell pressure, and water tank load. So first let's apply the masonry wall loads. I have discussed about calculation of masonry wall loads in our residential building design playlist also, and I have created one small table here. Let me go to that table. Masonry wall load you get by multiplying unit weight into thickness into height. So for external walls, I have supposed the thickness to be 0.25 meter, including that of plaster, and the height will be the height of our floor, that is 3.6 meter, minus the depth of our beam, which is 400 mm. We get the height to be 3.2 meter. Hence unit weight 19.6 into 0.25 into 3.2 is 15.68. Similarly for internal walls, which are half brick walls, the thickness will be 0.15, others will be the same. So 19.6 into 3.2 into 0.15 will be 9.41. If there are openings in our external and internal walls, then I have considered those openings to be nearly equal to 20%. So our load will be 80% of the total load. So 19.60 into 3.2 into 0.25 into 80%, we get 12.55. Similarly for internal walls. For parapet wall, which is a half brick wall of height 1 meter, the unit load will be 2.94 kilonewton per meter. And for partition wall, the difference is that for partition wall, the height will be the floor height minus the thickness of slab only. Since these partition walls are not constructed along the grids, to find the height we have to subtract from the total floor height, which is 3.60 meter, the depth of our slab, which is 0.125 meter, and we get 3.475 meter. So the weight of our partition walls will be 10.22 kilonewton per meter. Let's go to our architectural plan, and we see that we have walls in all of these external walls surrounding the floor space along all the sides, and we have openings on all sides except this 1 and 2. We have window here, we have door here, we have windows in all other sides. Similarly, for our top floor, we have openings on all these sides of our floor space except along these two sides of our staircase, or let's say three sides. One, this side, this side, and here we don't have any openings. So what I will do is, let me go. I am in my first floor plan here. Select all stories first, and then select all of your beams with openings. So first here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and here also we have opening from staircase to come inside the room. So select this beam also. And now let's go to our uppermost floors. Select this 1-story option here and select these beams also. 1, 2, 3. Should I select this or not? Let me see. Okay, there is wall here also, so let me select this also. And let's go to our topmost floor. Okay, this is our topmost floor, so let's unselect this. Let's unselect all here, because there will only be parapet wall, not full height wall here. So let's go one step below. Let's go one step below, and on this let's unselect these first, because there will only be parapet walls here, and let's select these inside beams. And after selecting these beams, go to assign, frame loads, and distributed. It is our dead load, and the value will be, let's see, with openings we have 12.55, and then click apply. Okay, now let's select these two sides walls here. For that, let's save the model first. Let's save the model first. Let me close this here. Let's select all stories option, and then go to our plan view, plinth level, and let's select this beam here and here. Now let me add another window here for 3D. Now we have selected these two beams, but we don't want to select the beam for uppermost story here. So select this option 1 story and unselect these two beams. And after doing this, go to assign again, frame loads, distributed. Now apply full wall load. And the value is equal to 15.68. 15.68. Okay. Now after completing this, we want to apply the parapet wall loads. So parapet wall first will be in our the 6th floor. Here, 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 and here. And then on our topmost floor. All along the edges. Go to assign, frame loads, distributed, and now the value of our dead load will be parapet wall. We have 2.94. 2.94. Click on OK. So now I think the application of masonry wall load is complete because there aren't other masonry walls inside our building. There are some partition walls. Okay, there is one wall here along this grid where we have a let's suppose it is a masonry wall with opening but of half brick thick only. So what we will do is we will select, we don't need to select this beam on this floor level. Let's go below. We will select this beam 1, 2, 3, 4, 5, 6, 7, except this topmost part. Go to assign, frame load, and distributed dead load. Now with a value of 7.53. 7.53. Click on OK. So we have completed this masonry load calculation. And now let's apply partition load. There are two ways to apply partition load. One way is that either you can, for example, if we are to apply partition load here, either you can calculate the length and thickness of all these partition walls that are present in one slab here, and then do the same process that we did before, multiply the unit weight into thickness into height to get the value of all of these walls, add the value of those loads here. You will get the value of load in kilonewton, and then divide the value of that load that you get by the area of the slab. Then you get the uniformly distributed load in kilonewton per meter square, and that you can use as the value of partition load. Since that will take much time, what I will do is, for now I will apply a value of partition load equal to 1.5 kilonewton per meter square. I won't make any calculation, but if you want to do exact calculations, then you can proceed in that manner. Calculate the unit weight and load of all of these partition walls and divide by the area of this slab to get the value in kilonewton per meter square. So for now, I will apply the partition load. Let me see. For all other floor levels, I will except this ground floor level, I will apply the partition load in this slab and in this slab. And for our 6th floor level, I will apply partition load here. So what I will do is I will start from our 1st floor level. 1st floor level, there isn't any partition load. For 2nd, this and this. 3rd, here and here. 4th, here and here. 5th, here and here. 6th, here and here. And for 7th, only here. Okay, and then go to assign. Now it is cell load uniform. This is partition load is 1.5 in the direction of gravity. Apply and click OK. So after applying partition load, now let's apply live load. For live load, we have considered it as office building. Although we have considered it as an office building, it is somewhat an assembly building because people are assembling in this building to give exams. Students assemble here to give exams. And for assembly building, what we have is from IS 875 part 2, I have written some value of imposed or live load. That is, live load you will use 4 kilonewton per meter square on assembly areas with fixed seats. And for restaurants also 4 kilonewton per meter square. For office room, kitchen and laundries 3 kilonewton per meter square. For toilets and bathroom 2 kilonewton per meter square. For corridor, passage and staircase 4 kilonewton per meter square. For balconies 4 kilonewton per meter square. So let's see our architectural plan. Most of our architectural space is used as an assembly space for candidates, whether it is our exam hall or our waiting room. So what I will do is I will apply a live load of 4 kilonewton per meter square in all of these assembly spaces. So let's go to my first floor again. Okay, this is our first floor. Let's see in our first floor, in our architectural plan or our ground floor, this whole is an assembly space. And here is kitchen here, and then there are toilets stored here. So what I will do is I will select all of these spaces which are being used as kitchen, and in the floors above, let's see, except this space and here we will use as assembly space. So 1 2 3 4 5 6, yes, okay, again 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6, 2 5 6, 1 2 3 4 5 6, and on this floor 1 2 3 4. Go to assign, cell load, uniform. Now this is live normal. So live normal is 4 kilonewton per meter square. Apply and OK. Now in other spaces, let's go to our ground floor. Here we have kitchen, and for kitchen the value of our loads will be, let's see here, for kitchen 3 kilonewton per meter square. So select this and go to assign, cell load, uniform, normal of 3 kilonewton per meter square, and OK. We haven't applied partition load, so what I will do is I will apply the let me check if I have applied partition load or not. Go to display, load assigns and cell load and partition. Okay, I haven't applied any partition load up till now. So I will select the slabs on which there is partition load. First, on ground floor we have in this slab here, and for other, okay, let's see again here, okay, here, and for other floors we have partition load on this slab and here, here 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 and here, and on our last floor we have partition load on this slab, so here. here, not here, sorry. And then go to assign cell load uniform partition load 1.5 kilonewton per meter square. Now what we are seeing in our architectural plan is that there is a storeroom here also. This slab is being used as storage. Now we have to apply storage live load. We have to apply this separately because NBC 105 has separate factors for load combination and during calculation of seismic weight for storage live load. And for storage live load, we will use the value of, let's see here, let us suppose that this is also a storage live load of 4 kilonewton per meter square. So let us select these slabs here and then assign cell load uniform and live storage of 4 kilonewton per meter square and OK. Now let's go to our roof. On our roof, since it is an accessible roof, we will apply a live load of 1.5 kilonewton per meter square. 1.5. This is our roof live. OK. And for stair live, let's go to select properties and slab section. Let us select stair slab and close, and let us assign cell load uniform the stair live or live stair of 4 kilonewton per meter square and OK. Now finally we are left with applying the load for floor finish. I think we have applied all other loads. So floor finish load calculation I have shown in my presentation here. For floor finish, if marble is used, then I have got the value of floor finish to be 0.465 kilonewton per meter square if marble is not used, and 1.143 kilonewton per meter square if marble is used. Since it is, let us suppose that for now marble is not only used in our staircase slabs but in our other slabs also, where candidates sit and give exam. So let us suppose that marble or any other type of granite or any other floor finish have been used. So now first what I will do is select all this stair slab and slab 125. Then I will go to our roof and I will unselect these options. And I will unselect these cantilever slabs. And then go to assign cell load uniform, and it will be our floor finish. And the value of floor finish load will be 1.143 kilonewton per meter square. 1.143. Okay. And now for our slabs at the top or our roof, the floor finish load will be 0.465. Go to assign cell load uniform 0.465 and then click OK. So we have applied all of our loads: floor finish, masonry, partition. Now let us go and apply swell pressure loads. And swell pressure load will only be applied on our basement walls. For that, first save the model, and what we want to do is first select all these walls in the basement. For that, go to select properties, wall sections and basement wall. And we have to select this one shear wall also, since this is in the basement, and then go to show selected objects only. So this is our basement wall. Now how will swell pressure act on our basement wall? If you remember, if this is our basement wall, then our swell pressure will act like this. It will be maximum at the base of the wall and minimum at the top, which is 0. So if gamma is the unit weight of the swell, then the swell pressure at the bottom will be gamma into h, where h is the height of this basement wall, and the swell pressure at the top will be 0. So we have to we have to apply a non-uniform load on these basement walls for the modeling of the swell pressure loads. And these loads will be acting inside of the building, that is from outside to inside. So first let's check that direction. For that, what we will do is, let's go to our this set display option, and then object assignment, and for cell assignment let's select local axis and then click on OK at the bottom. Let's select this local axis and select OK at the bottom. So let's see here, our local axis, let's look at this blue line. It is okay, this blue line is coming towards this structure. This blue line is our local axis 3, and our local axis 3 is directed inside of the building, and this is the direction into which our swell pressure will act. So this is okay. This is acting outside, so we have to reverse the local axis, and for that select this wall, go to assign, cell, and local axis. Rotate angle from default orientation by 180 degrees. Apply. Okay, this is not working here. Let's see again. Okay, what is suitable here is to reverse this local 3 axis. So select all of these cells on which you have to reverse the local axis, here, 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 here. Since this blue line is indicating outwards, you have to change this to inside, since our swell pressure acts from outside to inside. And then go to edit cells and reverse wall local 3 axis. Now you can see all the local 3 axes are being oriented towards the inside, and that is the direction in which our swell pressure acts. Now select all of these basement walls, go to assign, cell loads, and non-uniform. Now let's look here. Our load pattern name will be swell pressure, and our direction will be in the direction of local 3 axis, not gravity, not local 2 axis, but local 3 axis, which is represented by this blue arrow. Now we have the formula for non-uniform load is load at any point x, y, z is ax plus by plus cz plus d, and x, y, and z are in the global coordinate system. Now let us suppose that the unit weight of our swell is 20 and our height of our building is 3.6 meter. So the pressure here will be 20 into 3.6 means 72, I guess. 20 into 3.6 is 72 kilonewton per meter, or kilonewton per meter square here. What we have to do here is we have to use the value of coefficients A, B, C, and D, and this value of these coefficients are kilonewton per meter cube. That means we have to use the value of unit weight of swell here. Okay, the value of, let's suppose that the value of A, which is this point here, this below point here, the value of A is gamma, which is 20 kilonewton per meter cube, and D means at the topmost here where the swell pressure is 0, so value of gamma will also be 0. And let's apply this, and let's see the loads that are being applied. Let us go to display load assigns on cell, and let's go to swell pressure apply. Okay, these are the loads that are being assigned or applied onto this structure. And then click on apply. Okay, it already has been assigned. Close. And go to show all objects. Assign, clear display of assigns. And then save this model. So we have applied the swell pressure also. Now last load that we are left to be applied with is the water tank load. For that, let us go to our topmost story, which is this, and suppose that our water tanks will be located here above this story, above this staircase cover. And you can either divide this water tank load into joint loads and apply the joint loads at these 4 columns here, or you can apply the uniformly distributed load also. Now let us suppose we have two 1000 liter tank capacity, 2 water tanks each with a capacity of 1000 liters. That means we have 2 water tanks standing on this staircase cover, and we have to apply the load of those 2 water tanks onto our slab. So for that, how we do is, so 2000 liter water above this means we have 2000 kg of water, and convert this 2000 kg into kilonewton per meter square. First convert 2000 kg into kilonewton. So 2000 into 9.81, you get is 19,620 Newton, divided by 1000 is 19.62 kilonewton. Let us find the area of this slab. You can see that the area of our slab is 20.84 meter square. So divide that 19.62 by 20.84, you get nearly 0.95 kilonewton per meter square. So select this slab, go to assign, cell load, uniform, and this is our water tank load of 0.95 kilonewton per meter square. And now finally what we will do is, we will suppose that there are masonry steps on our staircase, and we will apply the staircase steps load on these inclined steps. We have already applied floor finish and live load. Now we will apply load from our steps. So select these inclined cells here, one, 2, 3, 4, 5. Let's rotate this view. Okay, how we will do is, let's do it this way. Go to select properties, slab section and stair slab, select. Now we will deselect all the horizontal slabs here. Let's start from the bottom. Let's deselect this here. Let's deselect all our landing slabs. Okay, now go to assign, cell load, uniform. This will be our dead load. We have already discussed how to calculate staircase loads in our previous playlist also, and I have done the same way, and I have got the value of staircase load to be let's see how much I have calculated, to be 6.90, to be 1.47 kilonewton per meter square. So let's use 1.47. Click on apply. Okay, so let me close this model. So this is our completed model. We have applied all the loads also, and we have completed the modeling also. So now the next step to come is the analysis, and we will see analysis and design in our next lecture. Let's close out today's lecture here. Thank you.